Hello and welcome to the last topic of chapter 1, gradients. There are two types of gradients. The linear gradient. This terminology is used to address two situations where we have a series of cash flows that is increasing by a fixed dollar amount. So the cash flows are getting either bigger or smaller by always a constant change in terms of quantity, in terms of dollars in this case. And the other scenario is when we have that series of cash flows either going up or going down at a fixed percentage change. Okay, so this is the capital form of the Greek letter delta. But this is in capital form and it denotes change. Right? Change being equal to new minus the old. Right? And then percentage change. Okay? So it's either growing, let's say at 5% every year, or decreasing at, let's say, 4% every year. What is constant is the percentage change, geometric gradient. If that change is just measured in dollars and is constant, then we call it a linear gradient. So how do we compute the present value or future value in these scenarios? Let's look first at the linear gradient. And let's say, for example, we have a situation and let's say this is months that starts at $300, but so there is a base of 300, but after the first cash flow, so by year 2, let's say we have a $50 increase. So it's 350. By year 3, on the top of the previous cash flow, there's additional 50. And by year 4, basically we have 3 increments of 50 already on the top of the 300. So these kinds of scenarios are either given as such, or we are told that the cash flow for year 1 or month in this case 1 is 300, for the second month 350, and then 400 by the third month and 450 by the end of the fourth month. So when we see these cash flows, we have to immediately identify that there is a pattern, and that pattern being the $50 increments. That you can break it down like that. So let's start from the present value. What is the present value of this series of cash flows? Well, obviously, as I've been highlighting, you can compute the present value of each cash flow individually, bring them all here. This is fairly easy to do when we have just a couple of cash flows. But when we have a huge amount of cash flows, let's say like 400 cash flows, then it's very tedious, so we use shortcuts. So in this case of scenarios, when we see a pattern, it is convenient to split the gradient from the base. So here we have a base of 300. That's the amount at which the cash flow series starts. Those 300 are always there. So you can split that, envision this as already an annuity. And now we're going to learn a formula that transforms these growing cash flows into a flat annuity. Let's call it a prime. So what we want to do is pretty much envision this time series has been comprised of two annuities, one called A1, or just A to be consistent with that. Let's put it in red. So one annuity, the 300, and there is another annuity on the top of it called A prime. And once we have these two annuities, then we can either aggregate them, add them up every year because they're going to be constant, or compute the present value of each one of them separately. So note that this is dealing with end of the period cash flows. So the first thing I'm going to do is find this A prime, being the goal to transform this cash flow series that starts just one time period after the first one. So note that the increments only occur at time 2. Right? There is no increment here at time 1. We start from the base, and then only in the next period there is an increment. However, the formula that I'm going to show you transforms these cash flows that only start at time 2 up to the last time period into something that starts at time 1. Okay, so we're going to flatten this out into something that starts at the same time as the base. Okay? And according to the time theory of money, time value of money, it has the same value, either if you look at it in present terms or future terms. Now, this formula for the linear gradient, okay, so this A prime I'm trying to look at, it's equal to, okay, how much is the increment, the gradient, and then take into account this discount factor, 1 over the interest rate minus n divided by 1 plus the interest rate to the power of n minus 1. Note that this formula is not the present value of an annuity, is not the future value of an annuity. This formula, all that it does is to flatten out the gradient into something constant that starts one period before when it starts in reality, right? So it starts at the same time as the base of that cash flow series. So what is that equivalent amount? The gradient is 50. Let's say that the interest rate is 3%. Let's just put it here. Per month. So this will be 50 times 1 over 0.03 minus the n is 4. We are transforming this gradient into 4 annuities. 1, 2, 3, 4. Okay. Then divided by 1 plus the interest rate of 3%, raised to the power of n, again 4, minus 1. And this would give $73.15. So what we found out was, having this cash flow series, or having one having this cash flow series or having this one is equivalent. Now at this point, so this is what you have to do to transform the gradient into an annuity that starts at the same time as the first cash flow. And now here you can simply add them or compute to the present value of each one of these annuities separately and then add them up. For the sake of simplicity, let's just add them up. So these 3 timelines are equivalent, meaning they both have the same present value and they all have the same future value. They are equivalent. What we learned here was how to transform these changing cash flow, changing in a fixed pattern, a $50 increment, into something flat that is constant, an annuity, and that starts at the same time as the first cash flow. So having this cash flow series, or having $373.50 every month, has the same value. Once we are done with this exercise, you can compute either the present value or the future value. So this was the linear gradient, and assuming a 3% interest rate per month. Present value of an annuity is the annuity itself times its discount factor equal to 1 minus 1 plus the interest rate, which is 3% assumed here, to the power of minus n, which is 4, divided by the interest rate, whereas the future value of an annuity is equal to the annuity times the discount factor given by 1 plus the interest rate to the power of n, which is 4, minus 1 divided by the interest rate. And this would equate to present value of 1387.04 and a future value of 1561.12. How to compute the present value of annuities? We already knew, we already have the formulas, and remember that you have a summary of these formulas on page 21 of your textbook. The novel thing was how to transform something that was changing by fixed amounts into a single annuity with equivalent value, either from the present value perspective or the future value perspective. So this is the linear gradient, where the changes are done in fixed dollar amounts. Now let's look at the geometric gradient. Where there is a constant percentage change. Constant, typically when it's a constant variable, we put a bar in math notation, so that's what I'm trying to say over there, is a constant percentage change. Let's say we have same 4 months, starts at 300, but then is increasing by 10%. Okay, so 300 plus 30, then 330 plus 10% on the top of that, then 363 plus 10% on the top of that. So it's growing always by 10% on what was there. So this is plus 10%, this is plus 10%, this is plus 10%. And the idea here is somewhat simpler to compute, because we just have one formula, and this is given on page 18th of your textbook, and we have to highlight 2 scenarios. So what we have here was, remember, by assumption the interest rate was 3%, just keeping the same as in the previous example, 3% per month. And now the growth rate, let's use letter G, it's equal to 10% per month. Now we have 2 cases, as highlighted on page 18. If the interest rate is different than the growth rate, this is the formula to use. present value, it's equal to, they use the letter D for the starting value of the series, and then multiply that by this discount factor. 1 minus 1 plus the growth rate to the power of n times 1 plus the interest rate to the power of minus n, divided by the difference between the interest rate and the growth rate. That gives you the present value, where you plug the value at which it starts, so this will be 300. 1 minus the product between 1 plus the growth rate, this will be 0.1, right? 1 plus 0.1 to the power of 4 times 1 plus the 0.03 for the interest rate to the power of minus 4, and here 0.03 minus 0.10, which will give you a negative number here. Okay? But then the numerator is negative, so they cancel each other. The other scenario is, what if the interest rate is equal to the growth rate? Let's say the interest rate was 3% and the growth rate of the cash flows was 3% as well. Well, in this case, this formula reduces to, only thing that changes is the discount factor, so P equal to D times n divided by 1 plus the interest rate. No exponent. So here we're dealing with a scenario where the interest rate is different than the growth rate, which is the most common scenario, and therefore we would apply this formula, meaning that the present value would then be equal to 300, 1 minus 1 plus the growth rate of 10 to the power of 4 times 1 plus the interest rate of 3% to the power of minus 4 divided by 0.03 minus 0.010. This will give you 1289.3. $1,289 plus 30 cents. Now, in the textbook, you're going to note that there is no future value for a geometric gradient. So if I ask you to compute the future value of a geometric gradient, first you have to compute the present value and then find the future value of this present value. So you still need to use this formula, even if I ask you for the future value, as step 1. And then you do a step 2 using the mother of all formulas, where the future is equal to the present value 1 plus the interest rate to the power of n. So this will be equal to the 1289.3 times 1.03 to the power of 4. So the future value of this geometric gradient would then amount to 1451.12. So if you are asked for the future value, basically what you do is you still compute the present value. Let's visualize what we did. So using the present value, we found that all these at time 0 is worth 1289. And then there is a second step, which is to bring this 1289 to find the future value. Right? So bring that value alone forward. There's nothing here. And how much is that at time 4? 1451. So there's a two-step approach to compute the future value of a geometric gradient, something that changes by a fixed percentage. So this is it for gradients, and that was the last topic of chapter 1. Now moving to chapter 2.